So far, we have installed Kafka Connect, configure workers, and learn how to install connector plugins. Now it's time to look at one of the most important parts of operating Kafka Connect in production, the REST API. The REST API is the primary interface for managing connectors rather than manually editing configuration files or restarting workers. Almost everything you do in day-to-day operations is performed through HTTP requests. Whether you are creating a new connector, checking its health, updating its configuration, or deleting it entirely, you will use the REST API. In this lesson, we'll walk through the complete connector lifecycle using the REST API from development on the way through monitoring and maintenance. This diagram provides a high-level overview of the operations available through the Kafka Connect REST API. Notice every request starts from a REST API client. That client could be a simple curl command, a monitoring application, a deployment pipeline, or even your own custom management portal. The first operation is post, which creates a brand new connector. Next is get, which allows us to retrieve information about connectors, including their configuration and current status. Put is used whenever we want to update an existing connector or perform actions like pausing or resuming it. Delete removes a connector completely. There are also special operations such as restarting connectors or individual tasks. What's important is that every one of these requests ultimately goes to the Kafka Connect cluster. Earlier in the course, we learned that a distributed Connect cluster shares its state through Kafka internal topics. Because of that, every worker exposes exactly the same REST API. That means it doesn't matter which worker receives your request. If you send a post request to worker 1 or worker 3, the request will be coordinated across the cluster and every worker will eventually see the same connector configuration. This greatly simplifies administration because clients don't need to know which worker is currently running a connector. Let's start with the most common operation, creating a connector. Here we are sending an HTTP post request to the /connectors endpoint. The request body is JSON and contains two main parts. The first is the connector's name, which uniquely identifies it within the Connect cluster. The second is the configuration object, where we define all the connector specific settings. For example, we specify the connector class, which tells Connect what plugin to use. We define task.max, which determines the maximum number of tasks Connect may create for this connector. Then we provide connection details such as the database URL and any other connector-specific settings. The nice thing is that regardless of whether you are creating a JDBC connector, an Elasticsearch connector, or an S3 connector, the overall structure of the REST request remains the same. Only the configuration properties change. After the connector is successfully created, Connect immediately returns a response. The response includes the connector name, the configuration that was accepted, the connector type, and an empty task array. Many people are surprised that the task array is empty. The reason is that connector creation and task creation are separate operations inside Kafka Connect. First, the worker validates and stores the connector configuration. Then, asynchronously, the Connect framework determines how many tasks should be created and assigns those tasks to workers in the cluster. This means the REST API can acknowledge your request almost immediately, while task creation continues in the background. If you want to know whether those tasks have actually started successfully, you will use the status endpoint, which we will see shortly. Once connectors exist, the simplest GET request is retrieving the list of connector names. Calling the /connectors endpoint returns a JSON array containing every connector currently deployed. In this example, we can see three connectors: a MySQL source connector, an Elasticsearch sync connector, and an S3 sync connector. Notice, this endpoint only returns the names. It's useful when building dashboards or administration tools because you can first retrieve the connector list, then query each connector individually for more detailed information. If we need to inspect a particular connector, we can request its configuration. Instead of returning just the name, this endpoint returns the complete configuration JSON that Connect is currently using. This is useful for troubleshooting because you can verify exactly what configuration is deployed in production. It also allows automation tools to compare the deployed configuration with the desired configuration stored in source control. If there are differences, the deployment pipeline knows an update is required. One of the most frequently used endpoints is the status endpoint. This tells us the health of both the connector itself and every individual task. Notice the connector has its own state. In this example, the connector is running on worker 1. Below that, each task also has its own state. Task 0 is running, task 1 has failed, and includes a trace field containing the exception that caused the failure. This distinction is important because a connector may still exist even if one or more of its tasks have failed. Instead of simply knowing that something is wrong, the status endpoint tells us exactly which task failed, which worker it was running on, and often includes the stack trace needed for troubleshooting. This endpoint becomes the foundation for monitoring systems like Prometheus, Grafana, or custom operational dashboards. This diagram shows how monitoring typically works in a production environment. On the left, we have a monitoring system. Rather than talking directly to Kafka, it sends a GET request to one of the Kafka Connect workers. The worker then reads the latest connector status from the internal Kafka status topic. After retrieving the information, it returns a JSON response to the monitoring system. The monitoring application then analyzes that response. If every connector and task is running normally, it simply recalls the health check and waits until the next polling interval. However, if one of the tasks has failed, the monitoring system can immediately generate an alert. Some organizations may notify an operation team. Others may automatically issue another REST API request to restart the failed connector or task, so the REST API isn't just used by administrators manually running curl commands. It's also the foundation for automated monitoring, self-healing systems, and operational dashboards. Eventually, you will need to change a connector configuration. For example, perhaps you want to increase parallelism by changing task.max from 3 to 5. To do that, we send a push request to the connector's configuration endpoint. One important thing to remember is push replaces the entire configuration. This is not a partial update. That means your request should contain every required configuration property, not just the ones you are changing. Once the new configuration is accepted, Kafka Connect restarts the connector using the updated setting. Because of this restart, there may be a brief interruption while the connector shuts down its existing tasks and starts new ones. We can remove it using a delete request. This immediately stops all tasks associated with that connector and removes its configuration from the Connect cluster. However, it's important to understand what delete does not do. It does not delete Kafka topics. It does not remove messages already written to Kafka. It only removes the connector itself and its associated configuration. Any data already stored in Kafka remains available for consumers. Sometimes we don't want to permanently remove a connector. Instead, we simply want to temporarily stop data movement. That's exactly what pause and resume are for. When we pause a connector, Connect stops processing new data and it keeps all of the connector configuration and offset information. Nothing is lost. Later, when we resume the connector, processing continues from the last committed offset rather than starting from the beginning. This is particularly useful during maintenance windows, database upgrades, or temporary downstream outages, where we want to pause in JSON without reconfiguring the connector. Sometimes failures are only temporary. Perhaps the database became unavailable for a few minutes. Maybe there was a network timeout, or perhaps an external system was restarted. Rather than deleting and recreating the connector, we can simply restart it. We can restart the entire connector, which recreates all of its tasks. Or if only one task has failed, we can restart just that individual task. Restarting from the last committed offset allows the connector to continue processing without losing previously completed work. Kafka Connect also provides several advanced REST API endpoints. We can retrieve the status of an individual task rather than the entire connector. We can ask which Kafka topics a connector is currently reading from or writing to. Another extremely useful endpoint is configuration validation. Instead of creating a connector immediately, we can ask Connect to validate a configuration file first. The worker checks whether all required properties are present, verify their values, and report any error without actually deploying the connector. This is particularly valuable in CI/CD pipelines because configuration mistakes can cause before they reach production. This diagram summarizes the entire life cycle of managing a connector. Everything begins with validating the configuration. If validation fails, we fix the configuration and try again. Once validation succeeds, we create the connector using a post request. After deployment, we continuously monitor its status using GET request. If monitoring detects a failure, we restart the connector or the failed task and continue monitoring. If we need to change the configuration later, we send a push request which updates the connector and restarts it. During planned maintenance, we may temporarily pause the connector and later resume it without losing offsets. Finally, when the connector is no longer required, we remove it using delete. Notice, managing a connector isn't a one-time action. It's an ongoing operational life cycle involving deployment, monitoring, maintenance, recovery, and eventually retirement. In real production environments, administrators rarely execute REST API commands manually. Instead, they usually wrap inside automation scripts like the one shown here. The script first checks whether the connector already exists. If it does, the script updates the existing configuration. Otherwise, it creates a brand new connector. After deployment, the script waits a few seconds before querying the connector status. Finally, it brings the connector current state so the deployment pipeline knows whether the deployment succeeded. This kind of automation integrates very well with tools like Jenkins, GitHub Action, allowing connector deployment to become part of your normal software delivery process. When managing connectors in production, there are several best practices to follow. If you are running multiple Connect workers, place a load balancer in front of the REST API so clients don't need to know which worker to contact. Implement retry logic because temporary failures such as network interruptions can occur. Continuously monitor connector health rather than waiting for users to report problems. Store connector configuration in version controls so every change is tracked and can be rolled back if necessary. Finally, automate deployments instead of relying on manual commands, making deployment more consistent and less error-prone. The REST API gives complete control over your connectors, so it must be properly secure. Enable authentication so only authorized users can manage connectors. Use HTTPS to encrypt communication between clients and the Connect cluster. Avoid placing passwords directly inside configuration files whenever possible. Instead, use secure credential providers or secret management solutions. Apply appropriate access controls so different teams only manage the connector they own. Finally, keep an audit trail of connector changes so you know who modified a connector, when it happened, and what was changed. Let's summarize what we have learned in this lesson. We use post to create new connectors. We use get to retrieve connector information, configuration, and operational status. We use put to update configuration or perform operation like pause or resume. We use delete to permanently remove connectors. We use pause restart operation to recover from temporary failure. Most importantly, the REST API provides complete lifecycle management for Kafka Connect and enable automation, monitoring, CI/CD pipeline, and production operations. This also concludes Chapter 3. We now cover installation, standalone mode, distributed mode, plugin management, and REST API operations. In the next chapter, we'll move beyond operating Kafka Connect and begin exploring how Kafka Connect works